Uh, all right. Hello, everybody. Welcome to our regular webinar series on vector symbolic architectures and hyperdimensional computing. Today, I have a pleasure of having Dominic Widdows with us, who will give a talk on quantum mathematics and artificial intelligence. So without any further delay, I leave the floor to you, Dominic. So please.
Right, thank you. So thank you very much, Evgeny, and thank you everyone for coming. And this is joint work with Kirsty Kitto at the University of Technology in Sydney and Trevor Cohen from the University of Washington. And those are the three of us who have written the particular paper that I'll be reviewing and going through in hopefully during the next hour. And it's a big area that a lot of people have contributed to in different ways. We'll certainly be touching on some of those. The paper in question I recently published on Archive, and it's under review at the moment. It's a later iteration of stuff that Kirsty and Trevor and myself have been working on for years. And so I think the work is particularly, say, timely at the moment because quantum computing is so much in the news and there's been so many developments there. So our goal today is to exploit some of the overlaps between quantum theory and AI. Well, that's our goal in general in this whole line of work. And the goal of this particular paper and our goal today is hopefully to make AI researchers confident about quantum computing, that quantum computing and quantum theory isn't this mysterious thing that has this, that there's this strange cat that's dead and alive and billions of dollars going into it and quantum supremacy, but we're not quite sure if things actually work. We're not talking about Schrodinger's cat here. We're talking about the mathematics behind it, some of which is really quite straightforward and a lot less confusing when we talk about it mathematically than we talk about some of the physical consequences of quantum theory. So I'm talking about mathematics. And why one of the reasons AI researchers should be quite confident in this area is we're talking about areas of mathematics that are a lot more familiar in artificial intelligence, a lot more widespread than maybe they were 20 years ago. Like when I started working in computational linguistics, you're working on statistics and vectors was very much a niche area, whereas now it's become really core to artificial intelligence. So the linear algebra is now familiar, but what's that got to do with quantum mechanics and quantum computing? Well, the key parts of that, and we'll be going through them in the talk, is that most people have heard a fair bit about, say, wave-particle duality in quantum mechanics, and so but less about vectors. So we'll be talking about how wave functions become vectors, because functions are a kind of vector, it can be thought of as such, how individual vectors generalize to slightly more elaborate structures, particularly density matrices, which we use for representing probabilities in vector spaces, and tensors that have become quite ubiquitous in AI under with libraries like TensorFlow. And we use them for the internals of training networks. But what are tensors and how are they related to quantum mathematics? And we'll be talking about, related to tensors, entanglement, which is quite easy mathematically, and we'll see why it's not something to be confused about. And hopefully we'll get excited about tensors being cheap and leading to potentially exponential memory capacity. When you add one qubit, every time you add a qubit, you double the amount of memory. That should excite anyone. And so these are results and the mathematics behind them and many of the applications are collected together in the paper. The archive link is right there. And then particularly for this community, for the vector symbolic architectures, I think one of the main takeaways I'd like to get across is that, our time is here, the time is now. It's possible to feel somewhat, bypassed by, neural networks doing everything, and we just need to give them more training data and everything will just become intelligent. Well, that's not going to happen. There's a lot of problems that we have with neural networks, making them scale, making them interpretable and to really understand and be able to reason about what's going on inside them, which isn't just a scientific task born of curiosity. Understanding what's going on inside neural networks is crucial for, I work in customer service. It's crucial for explaining how models did certain things, which we need to be able to do to make sure that they do good things and don't do bad things. And the concepts in vector symbolic architectures, particularly how superposition and sums and multiplication, binding can work together, are very important now for ways of modeling and understanding how systems are put together. So that's our goal for today. And the outline of the talk is, we'll discuss how quantum theory and AI both use vectors. And quick intro to vectors in quantum theory, very quick in AI. I suspect people are very familiar with that. And then we're going to start talking through what quantum structures are available that aren't used yet or very much in artificial intelligence. And I'll go back a little bit again, starting in the early 2000s. One of the criticisms that was often made of the vector models in, say, latent semantic analysis, term document matrices with singular value projection, was that they are so-called bag of words models. All we were doing to create, say, document vectors from word vectors is adding them up as a weighted sum. And criticisms like, well, you can't even represent negation that way. Well, that's true, but there are all sorts of other operations available in linear algebra, in vector spaces, beyond just vector sums and scalar products. And that led to a whole load of questions about how could we exploit those structures for doing semantics or representing meanings, getting useful outcomes. So we'll tell some of that story and look through examples in initially information retrieval was one of the first, and how projection operators can model logical connectives in models of information retrieval. Well, go on from there to modeling categories and implication. And that brings density matrices into the picture. And move on from there to composition and tensor products. So not just representing a lot of similar things and how do you make a category out of them, but potentially representing a lot of different things and how they go together to make a sentence. And there we'll discuss, I hope to have some time to dwell on the tensor products a bit, because tensor products are very common in AI now. So they're used in artificial intelligence, they're used in quantum computing, and they're used in physics a lot. And so to try and make that area familiar, which is partly just joining some dots, there's a lot of work on quantum probability, and particularly some recent work in statistical algebra that I hope to have time to draw people's attention to. And I'll touch upon quantum computing as well. Where are we in March 2021? Because a lot has happened in the past couple of years. I think part of that's a lot of what's making this work particularly relevant and interesting at the moment. I think that probably no secret that when Trevor and Kirsty and I first tried to write and submit a paper on this topic, I think it was difficult for people to receive because it really did sound like we were crackpots. And I think certainly in the past 10 years, the notion that there is a link between what we can do in quantum mechanics and what we can do in artificial intelligence doesn't sound as much like science fiction, because we have real quantum computers now, and there's a whole industry trying to figure out what to do with them. So we've been doing this for a while, but we're now part of something much bigger. Okay, vectors in artificial intelligence. I'll skate over this very quickly because I suspect it's really, really familiar to this audience. So we started with term document matrices as one of the earliest examples from the 1960s. You count how many times each term occurs in each document, and then you can add the rows together and you can weight the rows. So, hey, you've got vectors. The pixel values in a grayscale image, feature vectors in supervised machine learning, or any number of projection, analysis, reduction techniques also work on vectors. And the outputs and the internal states of neural networks are represented in terms of vectors as well. I think this might be one of the familiar but unemphasized stories of the past 10 years, is that one of the reasons we have been able to go so quickly in neural networks with things like understanding convergence, how stochastic gradient descent works with Jacobian matrices, and so it is based on a lot of prior results in linear algebra, because there have been all sorts of reasons for understanding and decomposing matrices for a long time. And so those techniques are very useful and very important, and they've been applied to new things in the past 5 years, but there's been a lot to go on. And so to look at it a different way, actually, we could ask the question, well, actually, if all these things are vectors, what aren't vectors in AI nowadays? Okay, well, we still have things like there are discrete sets, which are not in themselves vectors. You can build free vector spaces on top of them very easily, of course, but they're not vectors themselves. Or spaces with curvature. I can't start writing down latitude, longitude coordinates and adding them together with as if they're vectors and expect good things to happen, because they're curved, we run into singularities. So there's, and my background's originally in differential geometry, so of course that space fascinates me. But it's not what we're talking about today. We're talking about vectors. So what might be less familiar, and I'll dwell on this a little bit, partly because I found that what do vectors have to do with quantum mechanics is less familiar to people in AI. We're used to waves and wave particle duality. I think we're used to the science and the history of science literature that tells us about things like the Electron Two-Slit experiment, where we discovered, or where Davison and Germer back in the 1920s discovered that electrons interfere with one another. You don't expect that with particles. You expect them to bounce off and then go. You don't expect interference fringes. That even a single electron can interfere with itself if you're not watching it closely. And this is explained, or this is modeled by saying that a particle has a wave function and that collapses to a pure state, which is known as Born's rule. Born's rule is that the wave function will collapse to a pure wave based on the probability of that will be based on their wave functions are represented as vectors. And we know that measuring one property affects measuring others. That's Heisenberg's uncertainty principle. So the Born rule, how do we represent waves as vectors in the first place? Well, then we're going to go back from the 1920s to maybe more like the early 1800s. The techniques for this had already been developed. So the Fourier series is a way of writing a wave as a weighted sum of basis states. We start with a fundamental harmonic and then a higher harmonic and then higher harmonics on top of that. And you can make an approximation of a square wave out of a load of harmonic waves. And this isn't just for single dimensions. By the mid or late 1800s, we'd found ways of doing this in 3 dimensions with spherical or cylindrical coordinates. And so the notion that whatever, for a variety of different spaces, you can analyze functions on those spaces as superpositions of these fundamental waves. And you can look at the coefficients in front of those waves, this 4 sine theta over pi and 4 sine 3 theta over 3 pi, and think of each one of those as a coordinate. And then we've got a big long list of coordinates. And to add two functions together, you add the corresponding coordinates. To multiply a function by a scalar, you multiply it, all the coordinates. And so functions are behaving like vectors. In fact, functions literally are vectors. And when you choose some sort of collection of harmonic functions or otherwise orthogonal functions, then you're choosing a basis with which to represent other functions as vectors. And this is very useful for in quantum mechanics, for example, solving the time-dependent Schrödinger equation. It's useful because, okay, we're not going to solve the Schrödinger equation in detail, but one thing I'd like everyone to do is look at it a bit and realize that all the operators there are linear, that if I multiply psi by 2, I'm going to multiply the left-hand side and the right-hand side by 2 because the differential operator is linear, the del squared operator is linear, the potential is just depending on the radius and the time. And so why that makes linearity important is because if A is one solution to the Schrödinger equation, one of the wave functions that satisfies it, and B is a different wave function that satisfies it, then lambda A plus mu B is also going to be a solution of the same equation. So by the time we got to the early 1930s, people like Paul Dirac and John von Neumann were realizing that whilst the science in terms of the physics observations that went into this were very much about waves and particles, interference fringes, the mathematics could be represented very effectively in terms of vectors. So a system's represented by a state vector. It has to be a vector in a so-called Hilbert space, a space with a scalar product and one where infinite series converge. I think I learned I shouldn't talk. The term Hilbert space can be confusing because most of the spaces that we're dealing with are finite dimensional anyway. So we could just call it a vector space with a scalar product. And we encounter complex numbers throughout in quantum mechanics. There are reasons for that. I'll come back to the complex numbers a tiny bit at the end of the talk if there's time. And the measurements, when we make an observation, we measure something, we put a number on it. That number could be the position in one dimension, or the momentum in one dimension, or three momentum coordinates. But a measurement is looking at the system and attaching numbers to it. And those outcomes need to be real numbers, so the operators need to be self-adjoint, and so that means equal to their own conjugate transpose. That leads to other results, that they have a spectral decomposition with real eigenvalues, and a measurement of a state gives one of those real eigenvalues, because one of the eigenvectors with a probability given by a scalar product of eigenvector and input state. One way to see it important is when you measure something twice, you do get the same answer. So when you measure a system, it collapses down to one of its eigenvectors, then it is in a pure state, and if you measure it again, you will get the same answer. And there's a whole notation invented by Paul Dirac, so it's called Dirac notation to this day. So we have this ket vector written, and now for online presentations, I'm still very tempted to point at things and realize, no, you can't see my mouse, you can't see my finger, oh dear, oh dear, oh dear. But hopefully you can see the ket vector psi and the bra vector phi, which a covector is a dual vector. It maps vectors to real numbers. We'll come back to duality with tensors a little bit. So the scalar product, and why they get called brackets, is you put them together as a bra and a ket, you have a bracket, and this gives you a number. And that's the scalar product. That's how Dirac wrote the scalar product on the vector space. And we'll often call the basis vectors 0 and 1 for a qubit that has 2 dimensions. And then there are other notations that come out of this. So, for example, the tensor product of 2 vectors, we just write by juxtaposing the two vectors. And so I put that slide in there just as hoping to make it a little bit more familiar. And when you see that Dirac notation, just think of it as a vector, because that's all it is. So that was our super quick introduction to vectors in AI and vectors in quantum mechanics. At this point, I'll say very obviously, this is a survey of an area, so I'll be covering things very quickly. There's a lot more detail to go into, but I'm hoping to just survey the area, and so we'll move swiftly on from that way too short introduction. So come to about the year 2000, and we have a very quantum mechanics and lots of applications in AI that are using vectors, that are using weighted sums of vectors for superposition, for adding things together, and that are using scalar products for saying how similar things are. So, for example, in quantum mechanics, we had so the probability that the psi is observed to be in basis state phi is given by the scalar product of phi and psi. The probability that a document D is relevant to a query Q is given by scalar product between Q and D. Well, how about that? They look like awfully similar presentations of something. And it's surprising how many decades it can take us to realize this. Maybe it's too obvious a observation to be particularly deep, or maybe people are just reading different books. But around 2004, Keith van Riesbergen's book, The Geometry of Information Retrieval, came out, that was about recognizing the similarity and developing it into a whole theory for how to describe information retrieval systems that also enables us to model conditionals, natural kinds, and implication using vectors. And because this is one of the problems for, say, a strictly Boolean set theory, that there's very little in Boolean set theory that says banana and rabbit is a more natural set than mouse and rabbit. And because there isn't an underlying geometric structure for the space. And so a lot of Keith's development of these concepts in the book is about how to put those things together and get an interesting theory of conditionals. And around the same time, and independently, I was stumbling on how useful some of this formulation could be for modeling negations and disjunctions using vectors. This came directly out of the challenge that, oh, well, bag of words can't represent negation. Well, it can, it just can't represent negation by adding things up. To represent negation, you need to take something away. And we did some experiments with that. And so what bound this together was the quantum logic, which at the time I didn't actually realize it was brought to my attention by a reviewer. I think Keith already knew all about it. But the notion goes back to the linearity of Schrodinger's equation. And if you have two different linearly independent solutions of the Schrodinger equation, then you have a whole class of solutions. So any of those can be proper solutions of this equation, and that becomes our logical disjunction. Well, now we've got a sum of two components with arbitrary coefficients modeling a logical disjunction. Well, that, in the geometric terms of, well, okay, if psi and phi are lines, then I just gave you the equation of a plane. And we can make a whole theory of points are contained in lines are contained in planes are contained in higher dimensional subspaces. And that gives us a whole lattice of subspaces of a vector space. And that was one of the realizations that led to the development of lattice theory. And the orthogonal complement behaves as a negation. So we have a full logic of subspaces and projectors, which Garrett Birkhoff and John von Neumann in the late 30s described as the logic of quantum mechanics. And this became a pivotal development in lattice theory and axioms of logic. It might not be the best logical description for quantum mechanics itself, because it doesn't represent products and separability and non-separability very well. But that's with nearly 100 years of hindsight. At the time, it represented non-locality very well, that people were very excited about. So what's special about quantum logic? Why is it a logic? Well, it has meets, joins, and negation, but it's non-distributive. I hope this diagram shows that to some extent, that I have lines A and B, and P is in the plane spanned by A and B, but it's not in either the line A or the line B. It's in between, but it is somehow in a combination or interpolation between them. So for example, if I were to say, oh, it's 20 or 30 miles from London to Reading, then I might be making a perfectly true statement. Even if it's 23 miles, then yeah, sure, it's 20 or 30 miles. Whereas if I say catch bus number 20 or 30 to get there, and you catch bus number 23, you probably got on the wrong bus. When we're talking about numbers discretely, or there are various ways we can talk where we are implying some sort of interpolation, and times when we're not. And quantum logic is a better model for the former. Classical Boolean discrete logic is a better model for the latter. And quantum logic is also non-local as well as being non-distributive. So what I mean by non-local is it's a projection logic that we can project P onto A or onto B or onto C, and it moves it through the space. And it has useful consequences, like it removes synonyms of unwanted terms in information retrieval. This was one of the first pieces of research we did with this quantitatively, that if I have a query for suit and it's getting all legal results rather than clothing results, I can remove the term lawsuit, but I can still get lawyer, judge, plaintiff, etc. if I just remove documents with those individual words. Whereas if we project the whole vector, the suit vector to be, we got rid of all the legal meanings at once and got left with nearly all clothing meanings. That was a fascinating result at the time. That was one of the things that led us to start talking to other researchers in this area and figuring out that we were stumbling on some of the same things. And so very fast forward through the information retrieval story, it's also been used for term weighting improvements and how do we come up with good indexing strategies for compounds. And there's a good book in 2015 by Malucci that surveys much more of the area. So let's move on to, I mentioned a little bit about modeling natural kinds and implications and categories. And a lot of Keith's book is about this and how we represent probability distributions over vectors. I've mentioned probability a little bit because one of the famous, well-known results about quantum mechanics is that it is a probabilistic theory. It tells us how likely it is that a state vector is going to be resolved into a particular pure state, or the ensemble of such observations over time. And then we could get into a discussion about Bayesian versus frequentist statistics and so on, which we don't have time for right now. But anyway, probabilistic theory, and is it about frequencies or individuals or ensembles? Much debate throughout statistics and throughout quantum mechanics. But so we can get a probability distribution for measuring for will something project onto a line? Is it going to be in this pure state or this pure state? What if it's going to be in one of this combination of pure states? Well, now we're talking more about projecting onto a plane. And so I can easily write, so the first of these matrices with just the one in the top left-hand corner projects onto the first axis, the first coordinate axis. The second matrix projects onto the coordinate plane spanned by the first two axes. And I can write down such matrices for any projection, provided we have the coordinate system right. And then there are ways that I can normalize those matrices, make sure that the trace adds up to 1, for example, and then they behave like probability distributions. Or in fact, there's a specific generalization of the Born rule that the probability of finding the vector psi in the state represented by this subspace, or in the space represented by this operator, is the probability distribution is given by this expression here, where we operate A on psi and then take the scalar product with psi as a covector. And so there's a whole, so those matrices are called density matrices. It's a generalization of a vector. And if you think about it as, instead of just the probability that, the probability that a state will project onto a particular vector is given by the distance just between them. The probability that a state will be resolved onto a plane spanned by a group of vectors, well, you have to take several of those vectors into account. And this is a mathematical methodology for doing that. I mention that here because it's been used for describing categories or hypernyms, initially in Keith's book, and now more quantitatively by the papers referred to in the paper by Bankover, Lewis, and some very interesting ways there of using error terms, building up an ordering of the operators used. And there's a lot of links with category theory that arise from that, which I might touch on at the very end of the talk. So from vectors to density matrices and categories is one of the ongoing stories here. Right. So let's go beyond categories. I treat categories as an initial form of composition. It's quite familiar in machine learning that, say, I mentioned a rabbit and a mouse. Well, if I have a rabbit and a mouse and a dog and a person, then we might be looking for the generalization mammals. Whereas if I'm looking for a rabbit and a person and a crocodile and a bird, I might be trying to form the generalization tetrapods. But if I'm looking for birds and bees and fruit flies, I might be looking for things that fly. And so what are the right ways of generalizing is a kind of compositional question. What's the appropriate way of putting these things together in a way that generalizes? But it's a kind of treat everything as similar form of generalization. More generally, we want to talk about composition, where if I'm saying Kim kicked the football, then I've got three different things there: Kim, football, and kicked. And we're trying to we would like to compose them together to be able to explain what happened there, to be able to model what happens when we put together Kim, football, and kicked to make a sentence, Kim kicked the football. And we know that some things are important there. You've got to get the order right, like the football kicked Kim. No, that's not going to work. We have to know which things are verbs, which things are noun, and how to put them together. So let's talk about composition more generally. It's become something of I think, a holy grail for distributional compositional semantics. We want to be able to represent stories from words. And back in the early 2000s, I think there was clearly a dichotomy or a gulf that distributional semantics was pretty good at representing individual things. You could give it a word, you could find similar words, you could use that to help build retrieval systems or classification systems. But we were restricted in putting things together. Logical semantics, by contrast, the sort of Boole, Frege, Montague tradition, was good at putting things together, but not very good at having an account for what the individual parts meant. So that led to the challenge, how should we combine these things? And to backdate that, that was very much in computational linguistics. And I think in AI generally, we should go back to the early 1990s for this, that Smolensky's work on role filler bindings, if you represent a sort of variable name as a vector and the value it takes on as a vector, you can combine those together to represent the fact that in this particular context, this role is filled by this slot, and use that to build more contextual systems. So how do we do that? Well, there's many ways, and this is where I hope it gets really interesting for the vector symbolic architecture community, because, oh, this sounds like it needs a binding operator. Well, yes, it does. Now, we're going to talk about tensor products. And tensor products have not been the most popular binding operator in the VSA community for a couple of reasons. They have like computational explosion. They get you up to n squared very quickly. That's one of the things. And tensors are not themselves vectors in the space you started with. So we project them down and do other things with them. But those are both surmountable problems. And so what I'm going to try and jump through quickly is, what are tensors? How do they make those problems surmountable? How does that mean that it's a really good time to be talking about tensors in vector symbolic architectures? So let me try and get through the second half of the talk quickly. Okay, so tensor products. What's a tensor? It's a product between two vectors that makes a space of linear maps. So in particular, the tensor product of the space A with the space B would be the set of linear maps from B to A. And it has the dimension of the product space is the product of the dimension of the input spaces. That's very important to contrast with the direct sum of vector spaces, which is based on the Cartesian product of the underlying spaces, where you add dimensions. The dimension of the space of linear mappings between two spaces is the product of their dimensions. If you think about this in terms of matrices, it's quite familiar that if I have n-dimensional vectors over here and n-dimensional vectors over here, then the linear maps between them are represented by m by n matrices. So the number of coordinates, coefficients in that is m times n. So a particular example, linear maps from a vector space to its ground field, the real or complex numbers. So by the ground field of a vector space, we mean the number system from which the coordinates are taken. So a vector with real coordinates is a real vector. A vector with complex coordinates is a complex vector. Any vector can be mapped back to its ground field in a number of ways. You could just say, oh, take the nth coordinate, and that is a mapping from the vector back to its ground space. Turns out to be a linear mapping, because if I double the nth coordinate, I double the projection back to the ground space. And so the set of or possible linear mappings from a vector space back to its ground space has the same dimension as the space itself. And that is called the dual space, the set of linear mappings from a vector space back to its ground field. And the elements of that space are called covectors or one-forms. And they're very important in quantum mechanics and becoming, I think, increasingly important in AI, but sometimes not talked about explicitly. So that's one of the things that we do go through in the paper in some detail to make that more familiar. And so another example, linear maps from A to itself have dim A times dim A. Well, that makes perfect sense. So they're square matrices. And column vector times a row vector can give you a square matrix with its outer product. All right. Tensor products have been important in different areas. They've been important in algebra starting in the mid-1800s for expressing rotations and dilations. And this becomes multilinear algebra. We're very familiar with matrix multiplication nowadays. I think sometimes a little bit too familiar, because the notion that you multiply this sort of Sudoku board of numbers with this list of numbers over here, and it does the same things as dilation or rotation, or that is a considerable abstraction or considerably useful trick with numbers that reflects tricks with geometry that is very important and easy to take for granted. And this led to the whole theory of multilinear algebra, and a lot of the stuff I've talked about, projections and writing down matrices for these and compositions and so on, all comes out of multilinear algebra. In physics, we have the notion that a tensor, though when physicists talk about tensors, it's more often in the sense of a tensor field, as in a function from each part of the space to something. So tensors are used in physics, but with a slightly different meaning sometimes. In machine learning and artificial intelligence, we've used tensor to mean an operator on other vectors or other tensors, and it often becomes, in practice, a multi-array in NumPy or Python with multiplication conventions about how it should deal with other multi-arrays, and which is nearly the same, but not quite, as the way it's used in algebra. And in quantum mechanics, tensors just happen. And I'll show that in a few minutes. Just quickly, tensors are genuinely a bit more than matrices. It's just a multi-array story doesn't quite work. So one thing with tensors easily is map a vector to its corresponding covector. We often think of vectors as column vectors, in which case row vectors, like dual vectors, are row vectors. And there's a familiar representation of the scalar product, which is the scalar product of two vectors is the transpose of one of the vectors multiplied by the other vector. You have a real problem then with the notion that tensors are really a fancy word for matrices, because you can't map a column vector to a row vector by multiplying with matrices. The reason for that is any column vector has, is a n1 matrix. And so whatever you multiply it by, you're only going to get M1 matrices out of it. There's no way you can get by multiplying a column vector by another matrix. So instead of just talking about matrices, we have this extra algebra to take care of with tensors that is very important for saying how is it acting on the other vectors, the other tensors it meets and binds with, and the sort of which numbers pair with which other numbers conventions in matrix algebra don't quite do that. You'll actually, you'll find reflections of that in libraries when we talk about multiplying two arrays. what exactly do we mean by that? And sometimes you have to be a bit careful in NumPy or Pandas or whatever about when you're doing this in practice, which axes are actually binding with which other axes. A multilinear algebra just takes care of that by talking about the type PQ of a vector, of a tensor, which is how many ingredients have gone into it. So I hope that little digression did more to set people's mind at rest that, okay, tensors are a little bit more than matrices, but I'm pretty comfortable with them. I hope it didn't have the opposite effect of saying, oh, Lord, it's getting really confusing now. I wish you'd never mentioned tensors in the first place. We'll see. It's all in the paper, so I hope that is useful. And why is it important for semantic composition? We've really come a long way since 2006-ish. There is a raft load of papers now on ways of using tensor products to model composition. And the one I'm particularly focusing on here is the work by Bob Kirker and various people who've worked with Bob over the past 10 years, particularly in Oxford, but in several places now. And on distributional, compositional, categorical semantics. I'm sure it's partly that they wanted to call something DiscoCat, because really, who wouldn't? Fantastic name, but it does stand for distributional, compositional, categorical semantics. And importantly, it's a method that combines syntax and semantics, where they use the syntax of the sentence combined using categorical grammar to explain the structure here over on the right. You see how the boxes are connected and the lines in between them. Each of those lines is explaining which part of one tensor should connect with which part of another tensor. So the thing I said about how you have to keep in touch with the types, literally mind your P's and Q's when dealing with tensors and make sure the right things connect to the right things. Bob and Alex Kissinger and their team, they do that by writing these things with diagrams, which is a lot easier to keep track of sometimes than multi-indices and the way we do it in algebra. So tensors have come a long, long way in those models, and they actually run them a bit on a quantum computer. We've also seen an explosion of the use of tensors implicitly within neural networks. So there are now famous models within the neural language modeling community called Elmo and now BERT. They're all named after Sesame Street characters. And here the tensors are used inside the network, and the library TensorFlow gets its name from you set up a whole network and you regard the input and output weights for each node as a kind of tensor. When you are training the network using backpropagation, then you're effectively figuring out how should I adapt the tensor at this particular node to get the best outcomes on the lowest layer at the end. And so that's a whole flow diagram of how the output you want from one vector should affect the tensors that have computed it along the way. That's very implicit, and there's a lot of success in those models, but there's also raises a lot of problems of how do we really understand how they work, and that's very pressing, partly for the sheer usability and debuggability and being able to take down bad results. And even in those tensor networks, how the tensor products are working and can we reason about and somehow symbolize that at a higher level. Even Paul Smolensky, who started some of the work on tensors in AI back in the 1990s, has a couple of teams producing papers analyzing this. So whether we're using tensors explicitly for grammatical semantic composition, or whether we're using them implicitly inside networks, or we're using them explicitly inside networks, tensors are part of the story. I'll say a tiny bit on relations and entanglement. Entanglement is one of the quantum confusing terms. Quickly, it's one of the things that makes us think of, oh, if we disentangled a photon over here, did Schrodinger's cat get shot in the box over here? That's not the kind of ontological question arising from entanglement I want to dwell on here. Entanglement just means we can build tensors from tensor products of individual vectors. I can take the outer product of a row vector with a column vector, and I can build a matrix out of that, but I can't build all matrices out of that. It's obvious that I can't build all matrices out of that because a square matrix has n squared entries, and a row and a column vector between them only have 2n entries. So I couldn't possibly build all matrices in this way, but I can build all matrices by superimposing sums of these things, and raises the question, well, how many pairs like that do I need? And that's what the rank of a tensor means in multilinear algebra. And where this makes intuitive sense for modeling relations in language, and the text became small here because I was trying to fit in a few examples, but if we look at the various, say we're trying to build a parent-child relationship, it's not really the product of a prototypical parent and a prototypical child. We can say Darth Vader was the parent of Princess Leia, Debbie Reynolds was the parent of Carrie Fisher, Lord Byron was the parent of Ada Lovelace. I think we can pretty safely say none of those are really prototypical parent relationships, but if we combine a lot of these parent-child relationships, we can successfully build a no parenthood. And we've done a lot of that in medical applications for building distributed representation of things like the treats relationship, A treats B, and then you get a lot of A treats B relationships and try and generalize and get more for the purpose of drug repurposing. And I have Max Born, Irene Helene, Olivia Newton-John in here. I just think it's quite important that everyone working in quantum informatics should know that Olivia Newton-John is the granddaughter of Max Born. But otherwise, just entanglement isn't spooky action at a distance, really, in this context. Entanglement is you can't get n squared coefficients from 2n inputs. All right. I promised I'd say something about why this symbolic architectures. Well, I hope that that message has kind of through just from the words I've been using. This is all about vectors, superpositions, various kinds of multiplication, binding operations, stringing those things together, making networks out of them, being able to try and perform experiments based on, well, are we getting things that are related or similar to the things that we were expecting? And this is the kind of thing that the vector symbolic architecture community has been building in different ways for some decades. So, whilst we may not be quantum computing experts or we may not be neural net experts, this is our language. It also involves aligning explicit symbolic composition with implicit some-symbolic, or what we might call connectionist composition. So a couple of slides ago, when I was talking about, hey, when we're building a representation for a sentence out of the individual words or word parts in that sentence, should we do that explicitly using semantic operations that are parallel to well-known syntactic operations in grammar? Or should we do it sort of implicitly where the network has just learned how to put these things together and different nodes just become associated with different things? Well, either way, people are going to want to investigate those things in a lot of detail. And we're seeing a lot of that the last 1 or 2 years. For example, the word neurosymbolic has definitely become a buzzword, and I think we can expect that to continue. And neurosymbolic architectures are precisely trying to find some formal symbolic interpretation that can be responsibly attached to a sort of more connectionist association. That's precisely the sort of thing the VSA community has worked on. And we have a lot of results on robustly using distributed vector representations to learn and reason about similarities between individual objects, pairs of objects, classes of objects. There's a lot that's been written on how robust vector representations are in VSAs for maintaining like knowledge of which parts went into which holes, modeling sequences, modeling relationships. And so the challenges that the neural nets community is coming to, and the quantum computing community are coming to, they're problems that fundamentally make sense to VSA researchers. Now, why are tensor products important in quantum computing? And I hope this will explain something and sort of end the talk by getting people excited a bit. And that we write phi psi juxtaposed for the tensor product in quantum computing. Supposing we have two particles, phi and psi. Now, the basis for their states, say they're both in a two qubit system. Each qubit has 2 dimensions, so it's an up-down decision. And I haven't talked about qubits in detail, but hopefully that is somewhat a tiny bit familiar to people. The thing about when you put those two states together in quantum computing, the basis for their combined states is all the combinations of the individual states. And if we add another particle, then we'll add an extra combination to all of those, and we'll end up with 8. It's not convincing when you start with 2 by 2, because 2 plus 2 is the same as 2 times 2. But if we carry on playing this game, I would run out of screen real estate, but you'd find that every time I add a qubit, so I add another collection of basis states, then I double the number of basis vectors. So the number of dimensions in the tensor product grows exponentially with the number of qubits. So that's huge if it works. Rather, in classical computing, it takes work to make a tensor product. You're making an n-squared matrix out of 2 input n matrices, so you need quadratic time, quadratic space to be able to do that. The notion that it is just the natural physical realization of the physical representation, or the natural mathematical representation for the physical system that happens when these two particles interact, is astonishingly different. So literally, if we can put together 10 qubits, we get 2 to the 10 bits, and we've got a kilobyte in just 10 qubits. Decoherence is a problem. How do you actually put 10 qubits together in a way that they maintain that coherent wave-like behavior? That's an enormous challenge. But if that challenge is solved, then we've got an incredibly exciting world ahead. And if my description has been slightly unconvincing in terms of where we get exponential complexity here, there is a board book for babies on this called Quantum Information for Babies, which I heartily recommend to those of you with and without small children. And even though this is a really difficult challenge in terms of decoherence, I think if there are a generation of scientific babies growing up with the dream of this from an early age, I find it hard to believe that it won't happen some way or other unless it's genuinely impossible, which we don't believe. We just believe it's technically very difficult. So if the tensor product becomes free and vector memory, every time you have 10 qubits, you have a kilobyte, then that's going to be game-changing for VSAs. Okay, I'm on the hour. I knew I'd run out of time. Mathematical topics still to cover. Quantum probability, probabilistic algebra. I really recommend Taden A. Bradley's research there. The whole story of how these matrices represent probabilities and what that tells you about the distributions of the underlying vectors and how they interact. That's fascinating. New results there coming out that might give us new ways of modeling probability distributions, particularly for language. Great stuff. Category theory behind all of this keeps getting more interesting. Bradley Kirker, Abramsky connecting the quantum and the tensor networks and the VSAs. And I mentioned complex numbers. So many of these results seem to work better with complex numbers. So why aren't we using them in AI? We could be using them a lot more. The old argument was, well, they don't really represent real things. Well, by the time we're talking about the internal states and weights within a neural net, yeah, there's a lot there that is already not very real. If they're more effective with complex numbers, then great, let's use complex numbers. And so time evolution, complex exponentials, they seem to use similar mathematics as some of the attention mechanisms in AI with the transformer architectures. Attention is all you need. And whilst we're good at optimizing things for particular objective functions, we don't have a system of like AI training learning where we're doing time into evolution by how do we preserve things? What are the constants of motion here? So none of that physics of conservation laws seems to be extant in AI yet. If there was something there and time evolution could work in the same way, then Lord knows that might be really interesting mathematically. So going from stuff that is definitely exciting right now to complex number time evolution conjecture. So what's next? Like as if I know. So much going on at the moment. It's really exciting. There's real experiments coming out on quantum hardware. We've had 30 years of quantum thought experiments in quantum computing. These are becoming real. There'll be bigger circuits. There will be hype. There's been a lot of hype in quantum computing, some of it really quite undesirable. It's good that it gets people excited, but it's bad when it misleads into thinking that we've done more than we have. But there will be, I hope, I/O advances. If we can get more memory into and out of these things, then the computation's going great guns, especially on problems where the input state is relatively small and computation is very large. In natural language, I'd like to think that syntactic parsing is an important one of those. It's more platforms, software development kits, more real cloud access. So if anything, I hope this talk has been enough to whet people's appetites and think, as more of these platforms come out and there's SDKs and accounts I can sign up for to play with vectors, then as vector symbolic architecture researchers, this is an ideal ground to get involved with, and you probably know a lot more about it than you realize. So I hope that's been helpful. And yeah, that was my talk. Sorry it's run over a little bit, but thank you very much for having to take questions.
Thank you very much, Dominic. Great talk. So now I open the floor for questions. Yeah, Ross.
Hey, Dominic. Good to see you again. Thanks very much for that talk. Dominic, I'm really interested in the relationship between explicit tensor representations and VSA from the point of view of then the implications for VSA. I'd like to get you to speculate on that a bit, but I just need to set it up. You were talking about the Smolensky 1990 work on tensor product representations. And I think the defining feature of VSAs to me is a commitment to projecting your tensor product back down onto the same dimensional space as the operands and the value for engineering reasons. So you've got a closure on this, the one fixed vector space. And you're then relying on Johnson-Lindenstrauss to preserve the relationships between proximity of vector angles. But you're also losing things in that process as well. And I think, to me, but you've got the much greater mathematical insight on this, what you're losing is that intricate bookkeeping in tensor arithmetic of keeping track of all the indices. And so whereas in tensor arithmetic, you can apply these things to any vector in the space. It seems to me that in VSA, the implication of losing that indexing is you have to rely on the values, that the set of values in each of the ranks must be in a distinct subspace or something rather like that, so that it then becomes non-general in the sense that it's sort of much more like cognitive, that the solutions you get have to have some sort of constraints on them and be internally coherent to be solutions. But yeah, so could you speculate a bit more on the implications of the differences between the two?
I'm delighted you asked me to speculate, because that leaves me sort of free to be unreliable. And I'd like to say that, and this should be very much a discussion. So I would like to say I'm probably one of the people here that's interested in this, but certainly not the only one, and probably definitely not the most expert on all, if any, of the areas. So people do jump in, turn this into a conversation. And so things to things to bear in mind, that the whole notion that, oh yeah, but once we put vectors together into tensors, we're dealing with a different space and things are no longer comparable. Isn't that a problem? And yeah, so yes, the comparing is definitely a problem. There are tricks you can play by saying, oh, I can naturally project a vector up to a tensor by taking the tensor product of it with itself. Okay, is that a useful thing to do? I can unproject tensor products back to their ground space, but there's no natural way of doing that. You have to pick a special coordinate system to be doing that. So then, well, where does the bookkeeping go? Does it go elsewhere? The most interesting work I've read on that recently, actually, I have it right here, is the Taylor Bradley thesis on that goes into some detail on the partial trace operations. So if we think of the full matrix as a joint probability distribution, then if we take its then how do we, if we take its product with its transpose and consider that a kind of marginalization operation, what information do we still have kicking around in that matrix that looks like the joint probabilities in the marginal probability distribution? And that's some fascinating work. In the Kirker et al. Distributed compositional semantics work, they have everything going into a single sentence space. So all the comparisons are between sentences, which is good, but I don't know that you could use that to build a retrieval system where you're comparing individual words with documents, for example. And so some things that were problems might go away with the engineering computational load reasons for avoiding tensor products are deeply important on classical computers and unimportant on quantum computers. So yeah, it would be super exciting if that just went away. But it would leave us with the problem that there's no natural isomorphism from a tensor product space back to its ingredients. And that problem is not going to go away anywhere, because that's just the multilinear algebra. And so the various ways that plays out in different theories, what practical consequences that remain from that, or should we be doing the Kirker trick of trying to say, well, everything's part of the sentence space? I don't know, but I'd love to hear what other people think about putting those ingredients together.
Yes.
Sorry.
Yeah.
No, Evgeny, carry on.
No. You want to say something?
No, I was just going to say that at a very sort of dull, non-mathematical level, one of the things that strikes me about VSA is the importance of these cleanup memories. So, I mean, I think one interpretation of that is that it sort of pushes it from an engineering point of view, like these dictionary-based systems. So effectively, what you're saying is that we're not particularly interested in the coordinate system. The underlying units are essentially meaningless. It's that we're interested in computations where we want to be able to decompose what results we've arrived at back into terms of vectors we already know about. And that if we can't decompose them into things we already know about, then it's not a useful solution to anything. So I mean, I guess it gets back to that point I was making earlier about cognitive systems. That, you know, whereas if you're looking at maths, you're saying, well, here's an operator I can apply to any vector or tensor or whatever in this particular space. But with this sort of more cognitive limitation, you're saying, well, really only certain combinations, certain subspaces of the overall space make sense, and that the computations then have to be in terms of, can we decompose something into into some sort of a coherent composition of what we already know about.
Yeah. Yeah. Yes, I definitely agree with all that, with some sort of backstory that the discussion, say, about coordinates and what do they really mean, and are we learning properties of the coordinate system or of really the underlying objects, and that question in classical mechanics led to the very fruitful notion of, well, hang on, I should be learning properties about the physical world, not the coordinate system. And that's where the notion of, oh, well, invariance, what things are true irrespective of the coordinate system, those are the things that represent physical reality, that, you know, give us laws like conservation of momentum or conservation of energy, culminating in the work of Emmy Noether, and that identification of, like, properties of algebraic systems, and that the, say, rotational invariance corresponds to the conservation of angular momentum as a physical reality. That came to, that's a sort of beautifully satisfying apotheosis of that work. And we ain't got nothing like that in computational semantics. We haven't even got a notion of what quantities should be conserved, really. But could we?
So I have one comment on, actually also on this question, you know, how you, I mean, it's of course very beautiful in the VSA binding operations usually that they are dimensionality preserving. And so under certain circumstances, one can actually prove some mathematical equivalence between the tensor product binding for sparse feature vectors and the dimensionality preserving binding in dense spaces. So we have a recent paper on that, actually.
Great.
And I can actually post a link to that. It's an archive.
Yes,
So that really shows sparse, actually for sparse vectors, you can compute in the tensor product, and you can do that in a dual dense space where you actually use a binding operation, which is just a Hadamard product and dimensionality preserving.
Cool. I would like to read that. I'm not seeing where should I look to see the link show up, or can we attach that as an email after? Okay. Evgeny, could you circulate that paper as an email after the?
Sure,
after the
of course.
Thank you.
I can do that. I will do that. Mm-hmm.
I'm just copying it in the chat. The link.
Oh, I finally found the chat window. Thank you. Okay, I've got it now, but others might not.
All right.
Basically, the proof technique uses a compressed sensing technique. So it really only works for sparse vectors. That is a caveat.
Mm-hmm. And mentioning sparse vectors, also on Ross's mention of cleanup memory, that so some of the more techniques in so-called quantizing neural net using as a computational optimization technique are very similar. They sound similar to me, that at different stages in the tensor network, they say, okay, we're going to effectively quantize this vector to these like slightly coarser representation, but the overall we don't lose from that.
Yeah, I mean, there's in particular for the cleanup memory, there's a lot of arguments to be said also for sparse vectors, because you can build much more efficient cleanup memories, content addressable memories. And yeah, I mean, we also propose a second. So I mean, so one solution to actually avoid tensor products is now really to go into dense, to represent the sparse vectors by dense vectors, by equivalent dense vectors. And then you can just do the Hadamard product for the binding. The other solution is to actually use a subset of sparse vectors which have a block structure. And for these sparse vectors, you can define a binding operation, which is basically, it's a blockwise circular convolution operation that preserves also dimensionality for these sparse vectors. But of course, you can then only use these as the vectors to compute with these block sparse. I mean, these vectors that have a block structure. So there is we didn't find a dimensionality preserving binding operation for general sparse.
Right, because once we start taking random sparse vectors and adding them together, we pretty soon end up with dense vectors, correct? Yeah,
you can't. That's another thing in superposition. You have to give up some of the sparsity. That's of course another problem to be careful about when actually doing VSAs in sparse vector spaces. But in general, it's hard. You cannot even define a good binding operation, even if you disregard superposition. If you just stay with k-sparse vectors, I think it's impossible to actually define a good and reversible binding operation that's dimensionality preserving. But it's possible for the subspace of the k-sparse vectors that have this block structure, using the old Tony plate circular convolution, but basically just do rather than global.
So the superposition in the block encoding is still sparsity preserving, because you just take the argmax, so you still end up with a sparse vector.
Well, it depends. I mean, if you just sum them up, you of course the sparsity is reduced, and then you can do some nonlinear things to make it sparser again.
Yeah, but I mean, I've done quite a bit of work recently using the sparse vectors, and they've got equivalent performance to the dense vectors in terms of binding.
Yeah, we have an example in this paper actually, where we compare it to a dense VSA. Performance is the same.
Yeah.
Do you have a paper on that?
No, but I've got some interesting results. It's interesting that they're not quite equivalent. They're equivalent over certain ranges, but I'll send you a note with some results, because I think it's quite interesting that they're not identical.
I think, I mean, we think a lot about sparse, computation with sparse vectors, because we want to implement this with neuromorphic hardware.
Yeah.
And we really think there is a problem to give up some sparsity. You might not have to do that. For example, if you do this in a spiking neural network, you might not have to give it up on the level of spikes. So the spikes can be really very sparse, but then you need some mechanisms within neurons that they can create these superpositions of these sparse vectors, which are then intrinsic.
Yeah. Yeah. So we're working with Kaushik Roy at Purdue University, looking at how we can implement these sparse vector representations in spiking neural networks. So I think we need to exchange notes. I did read your paper, by the way, so it's excellent. So thank you for that.
Thank you. Yeah, sure. Yeah. But another comment to Dominic, I mean, it's very interesting with these equivalent, basically that you can represent the functions by the vectors. And this is actually also something that we are currently exploring with kind of similar preserving encoding schemes in VSAs, that you get basically these representation spaces for functions in your vector space, and you can really exactly define what these functions are. They are, you know, Hilbert spaces, depending on the similarity preserving coding.
One comment I wanted to make is Chris Simkin. It is the superposition side of using VSA imports quite a few limitations, because there doesn't seem to be a way of doing iterative superposition. You rapidly forget the old content, and I find it hard to believe that the brain keeps sort of unnormalized vectors. What I do in my implementations is I keep an unnormalized copy of the concept, and if I want to add to the concept, I can then add another vector and renormalize. But I find it hard to believe that the brain does that. And then further, one of our applications is distributed computing. Got autonomous. You don't know the raw vector that somebody else is. You know, they only see the normalized vectors. So this capacity issue around superposition and building more and more complex concepts and being able to add to them is an issue. And I wondered about this quantum stuff and whether it would sort of help solve iterative superposition.
Fine question. We might get into the detail, like the actual implementation of that. Yeah, it would until you measure it, and then then you have the problem that we can only we can have all of this sort of superimposed complexity and different waves interfering with each other in clever ways with quantum computing. But then when you measure the system, all of that interference goes away as the state collapses, which I still don't think anyone can explain. And so designing quantum circuits so that you only destroy the bits you don't care about and can look at other bits again later. I haven't done any of that. I'm just not an expert on quantum circuit design or how that. So in order to address that question, we need to go more into the details of. So we've talked. I'll mention a bit about the sort of danger of quantum hype. We've had a lot in the past couple of years about quantum advantage, to the extent that we don't talk about the quantum disadvantages nearly so much, like you can't copy states. And that's a problem.
Right. So
I was just going to comment further. The superposition thing, it seems to me that the brain does lots of, modifying and adding to that it already holds. And the complex concepts, rather than them being chained binding type operations, seem to me surely the collections of sub-features, aka superposition. And when you try and use the VSA stuff in anger, and a new sub-feature arrives, you do have this issue of, well, how am I going to add it without destroying all the information? And as I said, I'm using cheats at the moment, like keeping unnormalized copies of my concepts. but it doesn't feel like the brain would do that. So just as an observation.
Well, I have a suggestion. So it looks like we have pretty much quite many common topics to discuss around this quantum mathematics and VSA. So why don't we shift the discussion into our mailing list? So please contribute to this discussion offline. And I guess now it's time to wrap up this webinar. So I would like to thank Dominic once again for the great talk. And it was quite unique in terms of number of attendees. So I think at top of attendance, we have had 31 participants, which is very good. And also we also got a record on the length of the webinar. So very good. I am very happy. So
that's good.
Yeah, by all means, I'm very happy having you here. And so I hope we will continue this discussion offline. So thank you very much once again. And thank you all for attending this webinar. So see you in 2 weeks from now. So, and I say goodbye.
Thank
Bye.
you.
Thank
Bye.
you.
Yeah, bye.